Horizontal uniform circular motion. When a car goes around a curve, there must be a net force towards the center of the circle of which the curve is an arc. If the road is flat, that force is supplied by friction between the tires and the road. So here we have the force on the car. Some of the friction force is acting on each tire. The force on the passenger sitting over here. And the passenger has a tendency to go straight. If the friction force decreases, the car tends to move more nearly in a straight line and may not make it through the curve. Right here, the cars are trying to do this, and you can see all the rubber being left because the car really wants to go this way. If the friction force is much less than the force to keep the car going in a circle, it could fly off the track and people will get hurt. This occurs when the car is going too fast. As long as the tires do not slip, the friction is static. If the tires do start to slip, the friction is kinetic, which is bad in two ways. The kinetic friction force is smaller than the static friction force. Also, the static friction force can point towards the center of the circle, but the kinetic friction force opposes the direction of motion, making it very difficult to regain control of the car and continue around the curve. Sketch a top and a front view of the car's motion. The top view shows the car moving in a circle with its acceleration directed towards the middle of the circle and the velocity tangent to the circle. The front view shows the three forces acting on the car. The friction force, F sub s, is in the direction of the acceleration, right? Because you're going around in a circle. Let's translate the X and Y free body diagrams to solve for the velocity that will keep the car moving in a circle. We'll use the front view over here. So in the Y direction, we have the normal force minus mg equals 0, so normal equals mg. The car's not bouncing up and down. In the X direction, we have the friction force equals ma. Friction force is mu s times normal. And since it's centripetal acceleration and centripetal force, we have mv squared over r. And note, this time we have the normal providing the centripetal force again. What is normal? We got it over here. It's just mg. The m's cancel out. Do a little more algebra. So if the velocity is less than this, the square root of mu gr, the car will move in a circle. Banking curves can help keep cars from skidding. In fact, for every banked curve, there is one speed where the entire centripetal force is supplied by the horizontal component of the normal force, and no friction is required. Let's figure out what that speed is for a given angle and radius of curvature. And if you don't know what this is, we're going to find out on the next slide. We still have the same top view over here, but here's a banked curve. Right, you're going around in a circle, the car is heading towards you, the acceleration is in this direction, and the car will come out of the page and then turn, in this case left, and continue to make a circle. Now, these axes are different than an inclined plane, as the car is not expected to slide down this plane. Instead, it has a horizontal acceleration to go in a horizontal circle. Most of the time, it is best to align the axes with the direction of the object's acceleration, just like the unbanked curve. When the curve is banked, there is a force that keeps the car moving in a circle without relying just on friction. Set up the axes with the x-axis pointing in the same direction, the radial direction, as the acceleration. The y-axis is in the vertical direction. And perhaps you remember from dynamics, when we had objects sliding down, we rotated the coordinate system, but that's because the acceleration was in the down direction along the incline. This time we don't have that case, so we don't have to rotate our coordinate system. So sketch the free body diagram, and we're going to assume that no friction is necessary for the speed being used in the solution. The force that will be used to keep the car moving in a circle is the radial component of the normal force. So we're going to have to resolve this guy. And here's the radial component, or x component. Now we'll resolve the forces that don't align with an axis. In this case, there's only one such force, the normal force. The gravitational force is just fine along the y-axis. We're going to use this angle here as theta because that equals the incline here. So if you do a little geometry, you'll find those angles are the same. So this time we have Fn, the normal force, times sine theta along the radial axis. And we have normal force cosine theta going vertical. So in the vertical direction, we have the normal times cosine theta minus mg is equal to 0. Normal cosine theta is mg, so here's our normal force. In the radial direction, we have normal force times sine theta is ma. It's centripetal acceleration, so we replace a with v squared over r. Now combine the force equations for the vertical and radial directions to find the velocity of the car. We'll be taking this normal value and substituting it into this equation. So that's what we have here. And then a very fun identity here is sine theta over cosine theta equals tan theta. So g tan theta is v squared over r, once again, centripetal acceleration, and the velocity is the square root of gr tan theta. Solving banked curve problems with friction is more complicated. You can find a work-through example in the problem-solving presentation of this unit. A conical pendulum is a pendulum that sweeps out a circle rather than just a back and forth path. Since the pendulum bob, right over here, is moving in a horizontal circle, it can be studied as another example of uniform circular motion. However, it will prove necessary to resolve the forces as they are not aligned with the x and y axes. The angle theta remains constant as the pendulum bob moves in a circle. The length L of the pendulum also is constant. Draw a sketch of the problem and select axes so that one of them will line up with the acceleration of the object, the pendulum bob. Since the pendulum bob is rotating in a circle about the support point, the acceleration at all points is towards the center. The x-axis is then pointed towards the center, and then the y-axis is perpendicular to it. Add the forces to the sketch. We have tension along the string and the gravitational force pointing down. Resolve the tension force so that its components align with the x and y axes. So we have t cosine theta on the y-axis, t sine theta on the x-axis. The angle that t makes with the y-axis is theta, as proved by the alternate interior angles theorem. This guy is equal to this guy, alternate interior angles. Apply Newton's second law to the free body diagram in the x and y directions. The acceleration in the y direction is 0, as the pendulum bob moves at a constant height above the ground. The acceleration in the x direction is centripetal, as it is directed towards the center. Solve for the y direction first to find the value of t. Then substitute t in the x direction equation. So here's y, t cosine theta minus mg equals 0. T cosine theta is mg, and here's our value for tension. In the x direction, we have t sine theta equals mv squared over r. We replace this t with mg over cosine theta, and look what we get again. Sine theta over cosine theta. So that's tan theta. Little more algebra, and the velocity is the square root of gr tan theta. An alternative approach, and this is pretty clever, is to solve this as a vector equation using the sum of the forces as ma. This works when there are only two forces present, which of course is what we have. Translate the original vectors before resolving them to form a right triangle so that the sum of the two forces equals the new vector ma. And we'll show that on the next slide. The vector mg, which used to be down here, is moved up to here, and you're allowed to do that as long as you don't change its size and you don't rotate it at all. So the vector ma is going to point here, and we're going tip to tail with mg. So now we have a right triangle. So let's use tan theta is opposite over adjacent. So tan theta, and by the way, here's theta right here, just the same as this angle. So that's equal to ma over mg, ma over mg, or a over g. tan theta is also equal to v squared over gr. Why? We replaced a with v squared over r. And look, we get the same velocity again, square root of gr tan theta. That's good because the physics doesn't change, it's just the equations. Then you can use the Pythagorean theorem to find the magnitude of the tension. Right? Because we have, let's draw the triangle over here. We have tension here, mg here, and ma here. So T squared is a quantity mg squared plus the quantity mv squared over r squared. Take the square root of both sides, and we found the tension.